Hello, I welcome you all in this presentation related with the subject fundamentals of the manufacturing processes, and we are talking about the methods which can be used for improving the mechanical properties and the properties in general of the component manufactured. So since we are talking about the methods which can be used for improving the properties of the bulk materials, so among that it is about the heat treatment processes, and in the last few lectures we have talked about the fundamentals associated with the heat treatment processes, and also have talked about the full annealing process, or you can say the annealing process. Annealing is used in the different ways, and there are various terms which are used for the different purposes. Like one is called full annealing, which is primarily used for inducing the softness, reducing the hardness, and improving the machinability, especially of the high carbon steels. And then spheroidizing also softens the steels, especially medium and high carbon steels, and this spheroidization primarily takes place of the iron carbide, which in turn improves the machinability of the steels, apart from increasing the ductility and reducing the hardness. So about these two processes I have talked in the last presentation. Now we will see the other three processes like stress relieving process, stress relieving annealing for the stress relieving. Then there is a process annealing and intercritical annealing. And purposes of all these processes are different, and to understand these processes we need to talk these processes with reference to the iron carbon diagram. Say this is the lower portion of the iron carbon diagram, wherein the room temperature and the eutectic temperature, say corresponding to eutectoid temperature corresponding to 730 degrees centigrade. So to the temperature in y-axis, and in x-axis we have carbon percentage, weight percentage of the carbon, and here like say this is corresponding to the 0.8% carbon. So for the stress relieving purpose of the stress relieving annealing treatment is to lower down the residual stresses if they have been developed in course of the manufacturing processes like welding, casting, and the forming. Even very abusive or very rough machining process can also induce the residual stresses. These residual stresses in general lower the mechanical properties, adversely affect the mechanical performance with respect to the fatigue life and the toughness. Apart from that, they also increase the distortion tendency, and the dimensional stability is also reduced in presence of the residual stresses. So it becomes important to reduce the residual stresses being induced in due to the manufacturing processes, and for that purpose normally the component is heated to the temperature just below the lower critical temperature. So normally 600 to the 650 degrees centigrade is the temperature range which is used for stress relieving purpose. So whenever the steel component is heated to the high temperature, its yield strength is reduced, and reduction in yield strength eases the locked in strain, because of which residual stresses were induced. So basically the softening of the metal due to the heating at elevated temperature in range of 600 to 650 degrees centigrade for half an hour to 1 hour will be lowering down the yield strength of the steel, which in turn will be easing out the locked in strain, and that in turn will be reducing the residual stresses. This also causes the recrystallization of the steels. Then coming to the process annealing. Purpose of the process annealing is to reduce the strain hardening effect, which is normally induced in course of the manufacturing of the metals by the deformation based processes. We know that deformation based processes, if we work especially at the lower temperature, if you do the cold working of the metals in form of either wire drawing or like forging, then these processes induce a lot of residual stresses because of the differential, the deformation experienced by the metal at the surfaces compared to the inner core material, and that in turn causes the plastic means that causes the more severe work hardening at the surface as compared to the inner portions or in the core portion. So continued working or continued mechanical working basically due to the strain hardening increases the strength, increases the hardness, and but at the cost of the ductility. So we may arrive to a situation where increase in hardness and decrease in ductility can reach to such an extent that material may lead to the cracking, or even fractures can start in course of the during the manufacturing itself. So in order to induce the ductility and reduce the hardness during the manufacturing, in the manufacturing stages of the mechanical working, like after 1 pass, 2 pass, 3 pass, if we need further passes, then it may be required to go for process annealing, so that the work hardening effect can be reduced, and the hardness can be reduced, and the ductility can be induced. And for this purpose, again, the subcritical annealing is carried out, where heating is done below the lower critical temperature, around like say 550 to 650 degrees centigrade. So that will be reduced, that will be basically overcoming the effect of, or reducing the effect of, the strain hardening. Then coming to the intercritical annealing. This intercritical annealing will not just be reducing the residual stresses, but it also refines the grain structure significantly. So in which way the grain and the refinement of the grain structure in turn improves the mechanical properties. So basically, reduction in residual stresses, refinement of the grain structure, recrystallization of the grains, and improvement in mechanical properties is obtained when the intercritical annealing is carried out. And how it is done? Say the composition of the steel is corresponding to the 2.2% carbon, where roughly we have ferrite, 80% of the ferrite, and say 20% of the perlite. So in this situation, when the steel is heated from the room temperature, where basically we are having ferrite and perlite, on heating to the temperature up to the lower critical temperature, these two phases remains stable, but as soon as we cross the temperature, we cross the lower critical temperature, our perlite transforms into the austenite. So here this is the region where we'll be having ferrite plus austenite, and further increase in temperature will be leading to the conversion of the ferrite, or transformation of the ferrite into the austenite, and this will continue until this temperature is attained, means the upper critical temperature is attained. On reaching to the upper critical temperature, whole of the ferrite will also be transforming into the austenite. So what is done for intercritical temperature, intercritical annealing? Basically heating is done between the temperatures of upper critical and lower critical temperature values. So this is the range for intercritical temperature heating. So the temperature between the upper critical temperature and the lower critical temperature, heating is done between these two temperatures, so that what will be having in this case, alpha plus gamma, these two phases will be there in the steel. For example, at the room temperature, if the steel is having a certain amount of the ferrite and perlite, so this is the perlite at the room temperature, and this is perlite grain at the room temperature. On heating, both these perlite grains and some of the ferrite grains will also be converting into the austenite on heating up to the intercritical temperature range. So if we see the structural modification which will be occurring during the heating, these perlite grains will be converting into the austenite at this temperature. So this is what it will be leading to, that that other grains will remain as it is. So here like this grain will convert into the austenite, and this will also convert into the austenite, while other grains may remain the ferrite like this on heating to the just temperature just above the lower critical temperature. Further heating to the higher temperature, some of the ferrite grains will also be converted into the austenite. So once if we start cooling, means after heating and holding for some time, so that the homogeneous austenite is formed, we start cooling slowly, so that the fine perlite is fine perlite is formed. So the advantage is that whenever the heating is done in the intercritical temperature range followed by the cooling, it will be resulting in the refinement of the grain structure, especially when the cooling rate is little bit high. So intercritical annealing will be leading to the intercritical annealing will be leading to the refinement of the grain structure, relieving the residual stresses or reducing the residual stresses, and increasing the dimensional stability of the component after the heat treatment. Now another important heat treatment is the normalizing, which is primarily used for increasing the strength, hardness, and the refinement of the grain structure. Additionally, it also reduces the residual stresses if they have been introduced in the metal in course of the manufacturing. So normalizing heat treatment. For normalizing heat treatment, again we follow the cycle of the heating, soaking, followed by cooling. So cooling rates used in the normalizing case are a little bit higher than what is used in the annealing. So if the furnace cooling is carried out, usually in case of furnace cooling is carried out in case of the annealing, but in case of the normalizing, normally either still air cooling or forced air cooling is carried out. Forced air cooling is performed. So the cooling rates need to be used for normalizing a little bit more than what is used for annealing, and this is the cycle which is used for this purpose. So for the heating purpose, basically heating is done about 40 to 50 degrees centigrade above the upper critical temperature limit, after soaking to the sufficient time to homogenize the steel, followed by the normally air or forced air cooling is carried out. And if we see the same thing in light of the triple T diagram or CCT diagram, then for the different steels what we see here, like say this is the perlite start transformation line and this is perlite finish transformation line, and here we have temperature, here we have time in seconds, starting from like say 1, 10, 100, 1000, like this 10,000 seconds. So the slow cooling will be leading to the coarse perlitic structure during the annealing. So it takes a lot of time to cool down from the perlite start to the perlite end transformation time. But if we use somewhat higher cooling rates, then it will be taking somewhat lesser time. Higher cooling rate will be leading to the fine perlite structure. Further higher cooling rates can also be used for further finer perlitic structure. So this will be leading to the fine perlitic structure, which we can understand from this, like when we use annealing, then very coarse plates of the ferrite and cementite are observed, like this alternate layers of the ferrite and cementite. But when normalizing is used, very closed packed ferrite and perlite lamellas are observed, which offer improved strength and the hardness. At the same time, very refined structure is also obtained, and refinement in case of the steels with regard to the perlite is observed from the interlamellar spacing, like ferrite to ferrite or perlite cementite to the cementite distance. So with regard to the with reference to the normalizing, if we see, we use higher cooling rates, say normalizing leading to the using the higher cooling rate, resulting in the finer grain structure, which will be leading to the higher hardness and greater strength. Since the heating is done above the upper critical temperature limit, so this automatically softens the steel, because heating is done up to the austenitic state, and the softening of the steel automatically relieves the locked in strain, and which in turn reduces the residual stresses. So residual stresses, refinement of the grain size, grain structure is refined, very fine perlitic structure is produced, and these are the features which will be leading to the increased strength and increased hardness of the steel. So these are some of the key features related with the steel. Only issue is that in case of the carbon steels, air cooling may lead to the normalizing, but some of the steels which are offering the high hardenability and which we can understand from this diagram, like say for the carbon steel, our the CCT diagram is like this, where in CCT diagram is like this. So the critical cooling rate requirement is of this kind for the martensitic transformation. So this cooling rate is bit higher for carbon steels, but if we take the alloy steel, for which CCT diagram may be somewhat like this, for which critical cooling rate requirements are further lower, this may be corresponding to even air cooling, still air cooling rates. So this kind of the cooling rates which may be still even offered by the air cooling. And so for the alloy steels, even air cooling may lead to the martensitic transformation, or air hardening can occur. So this kind of situation we need to control the cooling rate appropriately, so that we go for normalizing only under the under the condition of cooling by air. So air cooling may not always lead to the normalizing, it can cause air hardening, especially in case of the alloy steels having the higher hardenability. So in that case we may have to reduce the cooling rate using suitable methods, which will be helping to reduce. Either we can use a hot air, or we can just cover the sample after soaking under the heat resisting materials, so that the cooling rate can be reduced and unnecessary martensitic transformation can be avoided. Coming to the hardening treatment. Hardening is also known as quenching heat treatment, and purpose of the hardening treatment is basically to increase the hardness of the steel component. And normally, say in annealed condition or in normalized condition, steel may offer steel of composition say 0.8% carbon content may offer the hardness of the 20 HRC in annealed condition. In normalized condition it may be 40 HRC. But after the hardening we may get as high as 65 HRC. So significant increase in the hardness is realized when hardening is carried out for the same composition of the steel. So steel offers such kind of the capabilities wherein the properties can be altered over a wider range by changing the structure. So for hardening purpose, what we do, the cooling rates are achieved in such a way that it is able to it is either equal to or more than the critical cooling rate required to avoid the formation of the soft phases. Say CCT diagram for a particular steel is of this kind. So like say one typical example of 4340 steel having chromium, molybdenum, nickel and the carbon. So in presence of such kind of alloying elements, we may find the different kind of the CCT diagram, and which may be like this. So these are the lines corresponding to the austenite. Here we have austenite plus perlite, here perlite, and this is where we have bainite, this is martensite. So there are different zones which are formed depending upon the cooling rates. So if the cooling rate is like this, we may get the coarse perlite. If the cooling rate is of corresponding to this one, then we will get the fine perlite. On the other hand, if we are passing through this zone, then we will be getting mostly the perlite plus bainite, and if also some of the amount of the austenite is left, then transformation will occurring into the martensite. So this will be leading to provide us the perlite, bainite and martensite. And if the cooling rate is corresponding to this one, then it will be leading to provide the bainite plus martensite. And here if the cooling rate is further higher, then it will be leading to the production of the martensite only. So there are different cooling rates for the different steels. There can be another CCT diagram for another steel wherein for simple eutectoid steel, if the cooling rate is like this, then we'll get the coarse perlite. If cooling rate is corresponding to this one, we'll get the fine perlite. If cooling rate is corresponding to this, then transformation, these are the transformation zone wherein we'll have perlite plus martensite. If the cooling rate is corresponding to this, we will have complete martensite, means transformation of austenite into the martensite, or perlite and martensite, fine perlite or coarse perlite. All that will depend upon the kind of cooling rates being imposed. So since the maximum purpose is the hardening of steel, so maximum hardness can be realized by having the complete transformation of austenite into the martensite, and for that it is necessary that the cooling rate being exposed is greater than the critical cooling rate. Critical cooling rate is the cooling rate corresponding to the rate at which it is able to avoid the soft zone formation. So it just passes through, or it is able to bypass the nose of the CCT diagram, so that whole of the austenite is able to transform into the martensite. Again, the complete transformation will depend upon the temperature of the quenching. For example, this is the MS temperature where martensitic transformation will start, and this is MF temperature. If it is quenched at this temperature, then what we will see here, so as per that, this if the quenching temperature is just at the MS, then we will have austenite is stable, but as soon as the temperature of the quenching is reduced, and if it is below the MF temperature, martensite finish temperature, then whole of the austenite will be able to transform into the martensite. So this is 100% martensite and this is 0% martensite, and in between we will be having the, like say, the 50% austenite plus 50% martensite lines. So if the quenching is done from the austenitic temperature to this temperature, then steel will be having in the component like 50% austenite and 50% martensite. If it is lower, then the percentage of the martensite may be 80 and 20% of the austenite. So whatever austenite is left in after the quenching to the temperature below the martensitic starch transformation temperature, that will be there as a retained austenite. So this retained austenite basically reduces the hardness of the quenched steel. Purpose is that for hardening purpose, it is expected that entire austenite will transform into the martensite. That's why the quenching is done at the temperature below the martensitic finish temperature line. If you have to do the hardening of the low carbon steels, then it becomes difficult as compared to the high carbon steels. Why it is so? To understand this, if we see this CCT diagram, for CCT diagram, high carbon steel will have the nose of the CCT like this, and while that for the low carbon steels it may be like this. So the critical cooling rates for the low carbon steel will be going in this manner. So low carbon steel, and the critical cooling rate for the low carbon steel will be going in this manner. So here the cooling rates for the high carbon steels are much lower. So this may be the situation where even air hardening will be sufficient for the complete martensitic transformation of the austenite into the martensite, while this is too high cooling rate for the low carbon steel. So the fraction of the retained austenite may be more or mostly it may have the fine perlite or the perlitic structure and little amount of the martensite. So not much high hardness can be realized through the hardening of the low carbon steels. Now we'll see the residual stress aspect related with the hardening. Like there are two variants of the hardening. One is the shallow hardening and another is the through thickness hardening. Let's take the through thickness hardening. Through thickness hardening or through section hardening. In this case, like from the surface to the center, if the hardness variation is plotted, then what will you find that in the through section hardness there is not much variation. The hardness almost remains constant. So this is the hardness and this is the distance from the surface to the center. Hardness by and large remains constant. And this may be like, say, in case of the hardening of the high carbon steels, it may be like, say, 60 HRC, which is by and large constant. But for shallow hardening, only the surface layers get hardened while the center remains soft. So in this case, in this case, for the shallow hardening, only the surface layers get hardened, and when it happens, what will be finding that the surface will be harder but the core will be softer like this. So this is the depth up to which it has been hardened, and below that it is softened. So when we find this kind of situation, so in case of through section hardening, we find the tensile residual stresses at the surface and compressive residual stresses at the center, while in case of the shallow hardening, compressive residual stresses exist at the surface while the tensile residual stresses exist at the center. So what is the reason behind this? When the through section hardening is done, because the cooling rates are high, the cooling rates are high and CCR, critical cooling rate, is low. So in that case, as soon as the surface comes in contact with the quenchant, it is cooled down first and it transforms into the martensite, which occurs with the increase of the specific volume. Since it is very hard and brittle, so while in case of the when the transformation from austenite to martensitic transformation occurs at the center subsequently, because like say in quenching, just within 2 seconds the transformation is occurring at the center, and after 10 seconds transformation is occurring at the middle. So the first transformation occurs at the surface, forming the martensite, which is very hard and brittle, and subsequently the transformation occurs at the center with the increase of a specific volume, forming the hard and brittle martensite. So this increase in a specific volume causes the development of the tensile residual stresses at the surface, because it cannot relieve the strain being experienced because of increase in a specific volume at the center, since it is hard and brittle. While in other case, just reverse happens. In the through section hardening, in the shallow section hardening, surface gets hardened, and subsequently when the transformation occurring at the center is doesn't occur transformation at the center from the austenite it occurs into the perlite or the benite, so it doesn't occur into the martensite. So since it occurs, since transformation at the surface occurs with the increase of a specific volume, but there is no major change in a specific volume at the center, so because of this we get that compressive residual stresses at the center, at the surface, and tensile residual stresses at the center. Now here I will summarize this presentation. In this presentation I have talked about the principles which are used for the normalizing and the hardening purpose. Thank you for your attention.